Hi everyone, today we're going to begin section 9-3, which is about exponential growth and decay. Today we're just going to focus on the exponential growth part of the section, and then tomorrow we'll move on to the decay. Exponential growth occurs when a quantity increases by the same rate, which is represented by the variable r, in each time period t. An exponential growth function is written in the form y equals a times the quantity 1 plus r all to the t power, where a is greater than 0, so a has to be a number that is more than 0 and positive. Y represents the final amount, that's the answer that you're solving for. A represents the original amount or the starting amount, so a is your starting value. R represents the rate of growth expressed as a decimal. A lot of these problems will give you the rate of growth in percent form. Hopefully you remembered it from 7th grade that to go from a percent to a decimal, you're going 2 spots to the left. So you move the decimal place 2 spots to the left. And T represents time. Okay, let's look at one example. It says the original value of a painting is $1,400 and the value increases by 9% each year. Write an exponential growth function to model the situation, then find the value of the painting in 25 years. So there's 2 parts to the question. The first thing we're going to do is write the exponential function. This is the form of the function. A, remember, is our starting value, which in this case is $1,400. And then the R is the percent written in decimal form. So the percent is 9%. If we move the decimal 2 spots to the left, it would be 0.09. And then finally, T is representative of time, and in this case, the time is 25 years. So what we're going to do is plug in these 3 numbers, the yellow, the blue, and the green, into the formula. When we do that, we end up with y equals 1,400. Again, that's the initial or starting amount, times the quantity 1 plus 0.09, which would become 1.09, raised to the t power. Now, the first part of the question, write the exponential growth function, that's what this is. We leave the variable t because then you can use this function to figure out the value of the painting in any amount of years. The second part of the problem is to find the value when t is equal to 25 years. So then you would rewrite the function with 25 filled in for time. And then again, you're allowed to use a calculator. If you have a scientific or graphing calculator, you can input it exactly like this and it follows the order of operations. If you do not have a scientific or graphing calculator, you have to do 1.09 to the 25th power and then go ahead and multiply by 1,400. Since we're talking about money, you always round to the nearest penny or hundredth place. So this painting that originally was valued at $1,400, since it's growing so quickly, in just 25 years, it would then be worth $12,072.31. Another type of exponential growth is compound interest. We learned about compound interest in 7th grade, but we did more basic problems last year. This year, we're going to add a little bit to the formula. Compound interest, hopefully you remember, is a common use of exponential growth. There's simple interest and compound interest. Compound interest grows much quicker because it is exponential. Simple interest is linear, so it does not grow as fast. The formula for compound interest is A equals capital P times the quantity 1 plus R over N, all raised to the N times T power. When we did compound interest in 7th grade, it was always really just time was in years and everything was compounded yearly. But that's not typically the case. If you have a savings account, right now you're typically getting your interest compounded every month. So you have to account for that in the formula. A is, again, the balance after T, the amount of years. P, just like last year, is capital P represents the principal, which is the original amount. The R is still the percent rate as a decimal. And then N is the added part here. N is the number of times that the interest is compounded per year. So what that means is if you're getting monthly compounded interest, then N would be 12 because it's 12 times per year. If it says it's being compounded quarterly, that's 4 times a year. If it said something like every 2 months, then that would be 6 times per year. So N is how many times in 1 year you're getting the interest. And T still represents time in years. Let's do a couple of examples of compound interest together. Again, the formula A equals capital P times the quantity 1 plus R to the n over n, all raised to the t times n power. Write a compound interest function to model each situation, then find the balance after the given number of years. So the first problem says $1,000 is invested at a rate of 3% compounded quarterly, and then we're going to write the function and then evaluate it for 5 years. When we do this now, the function again, it's I'm going to have a little trouble here. A equals 1,000 times the quantity 1 plus 0.03, because that's the percent in decimal form. And it's over 4, because 4 is compounding quarterly, means it's happening 4 times a year. And then this whole thing in parentheses gets raised to the 4 times t power, because again, the n is inside the parentheses as well as part of the exponent. That's the first part of the question. That's the actual function. And now we're going to evaluate it when t is equal to 5 years. So again, you follow your order of operations. All we've done here is just change the t to be equal to 5. And then when you work this out, you can always use a calculator. You're rounding to the nearest hundred or hundredth, which is the nearest penny. If you didn't have a calculator, you'd have to do this division first and then add the 1 to it, then raise that number to the 20th power in this case, because 4 times 5 is 20, and then multiply by 1,000. And the answer is $1,161.18. Okay, one more example. $18,000 is invested at a rate of 4.5% compounded annually for 6 years. This one's a little simpler because it says compounded annually, so that means it's just being compounded once a year. If we fill in the formula, the starting amount is 18,000. So that's the first part of the function. And then it's times the quantity 1 plus, and I have here 0.045, because 4.5% is 0.045. So that's the percent written as a decimal. And I don't have it divided by anything, because if it's being compounded annually, that means it's just being compounded once per year. Annual is once per year. You could put the whole thing over 1 if you want, but it's not necessary, since anything divided by 1 is just that number. You also could have a 1 here, but you don't need that again, because t times 1 is just t. And now if we're going to evaluate this for 6 years, we'll just rewrite it, changing the t to be 6. The 1 plus 0.045 is 1.045, so you're going to do 1.045 to the 6th power, and then times 18,000, rounded to the nearest penny. That's $23,440.68. Okay, you're now going to do some online questions about exponential growth, and then tomorrow we'll talk about the second part of this section, which is exponential decay. If you have any questions at all, please just let me know.